Hello students, this is a supplemental video on the side splitter theorem that was in lesson U5A04a. In that lesson I did not go over um, the derivation of this theorem, so I'm going to go over it right now because it may not necessarily be as obvious. To prove why the side splitter theorem works, okay, and again, just to review what the side splitter theorem was, it was um, it was saying that if you have an overlapping triangle, and the overlapping triangle, you can take a part of one side of that triangle and another part of that triangle. The ratio of those two sides, okay, on the left side, is going to be proportional to that of the ratio on the right. Whoops, I colored that wrong. It should be, well, I did get it right. It's blue up top and green on the bottom. So those sides, okay, will share those proportions. The only requirement is that the two triangles be similar. And in order for the two triangles to be similar, one of the bases have to be the same, which is why the start of this proof, I'm telling you that BD is parallel to AE. Because if BD is indeed parallel to AE, then we're going to have some corresponding angles that are going to show that the triangles are similar. So the first statement I'm going to say is triangle CBD is congruent to triangle CAE, and that is because corresponding angles are congruent. Next statement, I want to say that both triangles actually share angle C, and that is because of the reflexive property. So therefore, I can conclude that triangle BCD will be similar to triangle ACE because of angle-angle theorem. Now that I have those two triangles established as being similar, I can then set up the proportion. I can say BC, which is a leg of one of the smaller triangle, is going to be proportional to the longer to the same corresponding leg of the larger triangle AC, and that proportion is going to hold true for DC over EC. That seems fair, right? Because we understand this to be true because corresponding sides are proportional, right? Corresponding parts of similar triangles are going to be proportional. Okay, so we understand that that this proportion holds true. What is not obvious is that we have those sides that are split up. Okay, so how are we going to prove that? Well, I am going to show you that AC is actually made up of AB plus BC, and that's because of our good old segment addition postulate. And I'm going to do the same thing with the other side, which is for CE or EC, which is ED plus DC for the same reason. And without going through the statement of reason chart, because as we recall from one of the first lessons of this course, writing out the algebraic proof in a statement of reason chart can be rather tedious. I'm just going to show you the mathematics and prove why this works. So I can say, I'm going to perform a substitution. I'm going to say BC over AC. Instead of writing BC over AC, I'm going to write BC over AB plus BC is equal to DC over ED plus DC, and this is because of substitution between line 6 and 7 into line 8. It should be into line 5. This should say 5. Okay. Anyway, so once I get to this point, okay, I'm going to do a little bit of mathematics now on the side, okay? So I'm going to cross multiply over here, okay? And when I cross multiply, you're going to and distribute, okay, BC and DC into the respective parentheses there, you're going to notice something. You're going to notice that we have BC and BC times DC on both sides of the equation. So if I subtract them, okay, what will I end up with? I'm going to end up with BC times ED is equal to DC times AB. Look, I'm getting really close to the side splitter theorem. If I divide both sides by ED, and if I divide both sides by AB, I'll end up with what the side splitter theorem was. And hence, that's the conclusion of the proof.